All right, hello, and welcome to my presentation on artificial intelligence, or like artificial stupidity. And I'll get a little bit deeper into why that is the title of the presentation. It's not just a clickbaity title to make you all come and watch my talk. There's actually something behind it, and we'll get to that. Right, but what I'll be doing today is I'll be telling you a couple of stories about AI, about data, about machine learning. And some of these stories are success stories. Some of these stories show how successful AI and machine learning can be nowadays. But also some of these stories are the exact opposite. They are failures, and especially for those stories, I'd like to dig a little bit deeper into these stories and figure out why they failed, and then talk a little bit about what we can do in the future to prevent these failures from happening again. And when I say I want to tell you a couple of stories, there's the first thing that comes to my mind is one of the greatest storytellers that we had, which is Douglas Adams. And I'm sure some of you have read this book, The Ultimate Hitchhiker's Guide to the Galaxy. It has been it's relatively popular, especially in the tech community, and has brought us a couple of memes. That, for example, 42 is the answer to the question of life, the universe, and everything, and that we should not panic, and a couple of other things as well. And one of these other things that I would like to point out is it's not as popular as these two that I just mentioned, but it is a particular interesting example, especially in this context of AI and machine learning, and that is the Babel fish. So Douglas Adams introduced this Babel fish in one of his books, and this Babel fish is obviously a fictitious idea, right? It lives somewhere in this Douglas Adams universe. And this Babel fish has a fantastic feature. It's a tiny yellow fish, and if you take this fish and put it in your ear, the fish then picks up on the brain waves of the organisms around you, and whenever some of these organisms says something in their own language, the Babel fish then absorbs that and basically excretes it into your ear in a language that you understand. So what this Babel fish is practically doing, you stick it in your ear, and it translates every language in the universe around you into a language that you understand. Now, obviously, Douglas Adams was a very creative man, very funny as well. Obviously, this is a fictitious idea, and this fish does not exist. It's a crazy idea, if you will. But now let me show you something. If I now go to Google Translate, and there are other translate services, but I'm sure you know this one as well as some others. Let me show you something. Hallo und herzlich willkommen zu meinem Vortrag über künstliche Intelligenz. So I spoke in German, and as you can see on the right side, it has perfectly translated what I have spoken in German into English for you to understand. Admittedly, I came from this Babel fish example where you stick it in your ear and it picks up voice and actually speaks into your ear in a language that you understand. But I think this translation feature where I just speak in a language and it is more or less real time, translates it into a different language, is already a feature that we could have not imagined like a decade ago, 2 decades ago. It sounds almost like it would have sounded as crazy as the Babel fish idea. And obviously you say it's not quite the Babel fish that Douglas Adams has described, but I can show you something else. What Google is not only building this translator, this Google Translate, Google also has these earbuds. And these earbuds do exactly what the Babel fish does. It's not a fish, it's not yellow, and you still need a phone to translate. But what these earbuds do is you stick them in your ear, and then with your phone, it listens to the languages, to the text, to the voice being spoken around you, and does translate it and then speak it into your ear, just like that baby. So this absolutely crazy, fictitious idea that was described by Douglas Adams, that seemed unreal and almost unimaginable by most others, is more or less reality nowadays. And the reason why this is reality is because of machine learning that is powering the system. And there are multiple machine learning models. There's a model that picks up your voice and then translates it to text. There's a model that then does the translation. There's a model that uses the text and does text to speech again. And I think that is a wonderful example how machine learning can actually work quite well and can solve a relatively big problem that we didn't even think of solving earlier. And there are more examples where we know that machine learning has made a tremendous has had a tremendous effect on mankind. Like the couple of years ago, machine learning image recognition models started to outperform trained doctors in identifying cancer cells based on visual representation of cells, like there's picture of cells under a microscope. And machine learning models have started to outperform doctors by identifying these are cancerous cells or not. And I think it started with breast cancer a couple of years ago. I think last year, Google released a model that outperforms trained doctors on lung cancer. So and this is a use case. This is a solution that is literally life-changing. If we can detect cancer cells, obviously that person can get help faster if as if we would have not detected it, and if this machine learning models are more accurate and better at predicting it than doctors, then that is a clear step forward in a good direction, and it's a very valuable, literally life-changing addition. But I mean, I had the title. I added artificial stupidity to the title for a reason, right? Because and I'm sure we all have encountered some kind of situation where we knew there was some machine learning, some technology involved, and it didn't work out quite well. There were some bugs, and I have some relatively simple examples here on the right. There's a person on Twitter tweeting to Indigo, which is an Indian airline, and he's thanking them in a sarcastic tone for sending him to Kolkata and sending his baggage to Hyderabad. Obviously, it's sarcastic. You and I pick it up. And what I can only assume is some kind of AI that is answering for Indigo, and they reply they are glad to hear that. So clearly the AI has misunderstood the tone there. In the middle, there's someone complaining to PayPal that they got scammed, and again, I assume there's some AI that is going on, and they say, "Great, we're happy that you got scammed," and that is obviously another failure that a person would have not done in this particular situation. I mean, these are relatively simple examples. One of my favorite examples to show how AI has failed is this one. And if you speak Mandarin, you might already be able to figure out what is going on here. For everyone else, I give a little bit of a background. So there are a few cities in China that have introduced video cameras on zebra crossings, on pedestrian crossings. And basically, there's a traffic light that tells pedestrians, "Hey, I mean, if it's green, you can go. If it's red, the others go, and you have to wait." And what these cameras do is they record this pedestrian crossing, and if it is red and someone crosses, then obviously they're jaywalking. And then what is happening, and what you can see here is there's a big, I want to say gigantic screen next to the crossing, and then the person who's crossing gets like zoomed in and is showed, is like shamed, and say, hey, this person just crossed the street, even though there was a red light. This person just jaywalked. But if you now look at this photo of that screen, you can see there's actually not a person crossing. It's a bus driving, which has a green light. The bus is driving, and on the bus, on the side of the bus, there's a picture of a woman printed on it. And this camera, which uses image recognition to identify that there is a face on it, this camera has now identified the printed face on the bus as a person crossing the zebra crossing. Obviously, that is not a case of jaywalking. So another case where machine learning, which is the part of the image recognition, where it has clearly failed. And to give some context, so this woman was not even in this city. This woman was in a different city at that time where this got taken. I think she's the CEO of some company, and they advertised with her on the bus. But what happened was, not only did they display her picture on this large screen, they also sent her the notification on her phone. Because not only do they use image recognition to identify there is a person, they also have a database of faces, and they use face recognition to identify who that person is. So they saw this bus driving by, thought it is a person, figured out who that person is, and then sent a message to this woman, which at that point was in a different city, saying, hey, we just saw you jaywalking. And I think in this case, it was not the case, but in other cases, in other cities, it has even gone a step further, where the fine for jaywalking gets deducted immediately from the person's WeChat Pay account. Like there's, if you want a WeChat Pay account, you need a Chinese bank account. If you want a Chinese bank account, you need to identify yourself. That is how the person is then linked to the WeChat Pay account. And what they do is they figure out as a person, they figure out who it is, they figure out the WeChat Pay account, and then immediately within seconds deduct the amount that is the fee for jaywalking. From a technical perspective, this is a mind-blowing system. It's extremely interesting what is possible on a technical level. But if we look closer, and I think this example shows it quite well, the implications when it fails can be pretty bad. Like, I mean, this is a fine for jaywalking. How much can it be? But all of this is automated. All of this relies on the correct identification of a person and of the correct understanding of the situation, in that case being a jaywalk situation or not. And if we extend that to larger crimes, or crimes with where the punishment is different, then there is a lot of power in the relies on this accurate identification, on these machine learning models to work flawlessly without bugs. And we can already see that is not the case in some cases. So it's even though it's a technical marvel, I would say, on a different level, the question is the technology good enough to actually be applied here, or in the bigger sense, on legal measures in general. And I've said machine learning a couple of times already. I've said AI a couple of times. All these terms have been used a lot in the last couple of years. They are growing continuously. They've been hyped a lot by a lot of people. Most of the technology companies on their website nowadays have they're advertising that they're doing some kind of artificial intelligence thing to improve whatever they are doing. And I would like, at least for this talk, have a common understanding of what these terms actually mean, or what their definition is in my perception. And we can start with the artificial intelligence on the right. And I do like this definition. There are other definitions of artificial intelligence. I do like this one. And I think it is often also used for all the advertisement purposes, because it is very broad. And I'll read it out quickly. artificial intelligence is the theory and development of computer systems able to perform tasks normally requiring human intelligence. The important thing to note here is that there's no mention of any technical implementation. There's no mention of any technical way how this gets achieved. It is simply saying something where you would usually think a human needs to have intelligence, which is now done by a machine. And I'll give you an example to maybe make that point a little bit clearer. If you think about a chess program, a computer program that you can play chess against. Typically, if you play chess against a person, you would assume there's some kind of level of intelligence. So that checks the first box. And then we all know chess programs exist. So then it's artificial. So it would fit this definition. And now we look at the implementation. A possible implementation for a chess program could be relatively simple. You look at the state of the board, all the figures and all the positions that they're in, and then basically brute force all the different possible moves, and then the follow-up moves and the follow-up moves and their opponent's moves in response. And if you just brute force all the possible moves and the subsequent moves, at the end you pick a set of moves that leads to your to the outcome that you want, which is winning the chess match. But this brute forcing is relatively simple, right? Like technically, I wouldn't want to write it, but it's a couple of loops, it's a couple of if-else, couple of branches, and that's it. There's nothing nothing fancy from a software engineering perspective. So that is, and I think that is where it's often used in advertising, or it's often used nowadays, where artificial intelligence does not require a certain style of software. It is more the use case that defines whether something is artificial intelligence or not. So now when we move over to machine learning, and I think this is where it becomes interesting, really, machine learning is fundamentally different. Machine learning does not rely on an algorithm implemented by a software engineer. Machine learning, the outcome of a machine learning model is determined by the data that was used to train this machine learning model. If you train the machine learning model with different data, the outcome becomes different. Technically, there are some weights in it, and some things change over time, more data, other changes happen. But the general idea is that the outcome, the algorithm, the way how this machine learning model learns to decide at the end is not predetermined by the software engineer writing some code. Instead, it is the data that defines this. And that is fundamentally different than a lot of things we've seen before. Machine learning is also not new. It has just become really feasible with more processing power that we had in the last decade available. And then neural networks is a type of machine learning, a subset of it, modeled on biological brains, where you have like neurons and they have axons and they connect to other neurons and they're sending signals. And then there's deep learning, which is more or less only a neural network, but bigger. You have lots of different layers of these nodes, and a lot of nodes in them. Basically, if you have a lot of layers in your machine, in your neural network, then it is deep learning. And then there's another term which is data science, and that is just it can use some of these methodologies to then get insights out of data. So I think that is useful to have this common understanding for the purpose of this talk, at least. And I mentioned deep learning is just a big neural network. This is actually a simplified view, but the what I would want to show here is this one thing, that you can see that there are lots of different nodes, right, in different layers, and all of these nodes are connected to the nodes in the other layer. And this connection is more or less sending some kind of data. It is not a lot of data. It's basically saying, yes, I'm activated, or it's like some kind of number that you want to send, right? But the amount of connections that we see here, and it's like there are so many lines already that it becomes really difficult to understand what is going on here. And I'm telling you, all of them are connected, but if there were one connection missing, you wouldn't be able to see that immediately, right? So it's already really difficult to understand and see what is going on here. And the real life deep learning neural networks are significantly larger than this. They can have thousands of nodes, and they can have 50, 100, they can have hundreds of layers. So the amount of connections in them are also significantly more than shown here. And that leads to this one big problem that machine learning has, and there are multiple big problems. I'll be talking about two today. This is the first one, which is that this behavior is basically a black box. As a human, as a software engineer, as an ML engineer, it is really difficult, if not impossible, to comprehend why this particular machine learning model makes decisions in a certain way, why the output is a certain output based on something. Because it's just this, it's so complex that it becomes impossible to see. And that is where a lot of the problems that I mentioned come from. Like you can't really understand what's going on. You just hope that it works, and you have this black box behavior where you just put in data and hope the outcomes is correct. But that is only one of the issues with the widespread deployment of AI and machine learning models. I'll be talking about the other thing now, and I give you an example of this application. That in 2011, the city of Boston had a problem, and that problem was potholes. They had a lot of potholes all across the city on their streets, and they wanted to fix that problem. It was 2011. They did what everyone did when they had a problem. They wrote an app. And this app, called Street Bump, worked in a pretty smart way. I have to admit that. This app worked in the way that when you installed it on your phone, and when you were driving across, when you were going on a trip and you were driving across the city, you would open the app, put the phone on your passenger seat, and then drive around. And whenever you would encounter a pothole, there would be a bump, and the phone and then the app would realize, okay, there was a bump due to the accelerometer. So it would notice, okay, there was some kind of disturbance, and it would then take the GPS coordinates and send those GPS coordinates to the server and say, hey, this is where I encountered a bump. You might want to check if there's a pothole. And when there is a pothole, you might want to fix it. I think it's a pretty smart idea. And so they started this, they released the app, and after some time they realized, when looking at the map of Boston, they realized most of the potholes were in the high cost of living areas. Oh, and when you think about it, that's odd, right? Why would only in high cost of living areas be potholes? Like, why only where the rich people live? Why not in the rest of the city? And the problem here was that it was 2011. Not everyone had a smartphone. Not everyone had a smartphone where you could install an app. That was relatively new, actually. Only the people who had enough money, who could afford that, would have a smartphone. And only these people, and these people would most likely live in these high cost of living areas as well. So you were basically, I mean, nowadays every 5-year-old kid is watching TikTok videos. But 2011 was a different time. So what happened here was that the data was skewed. Like, the data only represented a subset of the population of Boston. And it was only the high income subset. And that's why the data only showed potholes in the high cost of living areas. And I must admit, the way they fixed this is equally smart. What they did is they then installed this app on phones and gave it to public buses and garbage trucks, and basically vehicles that were driving around the whole city street grid, and therefore they create like an actual coverage of the whole city. The important thing to note here, the important thing to learn from this particular example is, however, that there was no machine learning involved. There was no black box behavior that went wrong. It was solely the data that did not represent the actual situation. The data was skewed, and that's why this initially failed. So that is the second issue that I see with the widespread deployment of machine learning nowadays. It is that the data is biased, has a social bias, and that is difficult to see in the beginning. And then if you use that, you run into issues as well. And I can show you another demo. You remember this, and you might even remember the example that I'm going to do now, which was a couple of years ago that got popular. If I type he is a nurse and she is a doctor, and we all know that there is no reason why it needs to be he or she, right? We know every gender can be a nurse, and we know every gender can be a doctor. Now, if we translate this from English into a language that has gender-neutral pronouns, like Malay, Turkish is another one, then we lose this information, this gender information. Like this basically says that some person is a doctor, and this person says it's a nurse, but it doesn't say it's a he or a she, right? So now if we take this sentence, these two sentences, and translate them back into English, and keep in mind, I wrote he is a nurse and she is a doctor. We translate that back. All of a sudden, the retranslation reads she is a nurse and he is a doctor. Now, the reason for that is, even though I've called out Google Translate previously because it's working well, right? And I've explained how there's a lot of machine learning involved. The reason for this particular issue is that basically how these machine learning models, these translation models work is they read a lot of text. There's a machine learning model, and you feed in a lot of text, books in one language and in the other. And over time, the machine learning model, the translation model, learns, look, this particular part in that language translate to this particular part in that other language. So you train it with a lot of this data. And obviously, the text, all these texts were used to train. I mean, they are old texts. They are texts that existed, and a lot of these texts are historical in the way that they're not the latest. And historically speaking, for whatever reason, because for societal reasons, being a nurse was often associated with the female, and being a doctor was often associated with the male. And that is how this machine learning model has now learned to translate this sentence, even though there was no gender information in the original Malay sentence. The translated version includes a gender, and that gender is based on the historical data that was used to train this model. There was a couple of years ago that became popular the first time with the Turkish language, which also does not have gender-specific pronouns. And what Google then did is they created this double translation where they say, hey, look, we don't know what gender it is. It can be she or it can be he. The truth is that this for Turkish that had worked because it got popular, and then they fixed it for Turkish. For other language, it has not yet been implemented. And I also think that it's an additional extra effort that you would need to do on a case-by-case basis, which is not the ideal way if you consider the widespread deployment of machine learning models. There's another example where where it clearly shows that data being used to train a machine learning model can be pretty bad. If you don't remember Tay, I'll give you quickly a reminder of what this was. Tay was this chat bot in a way. Nowadays we call it chat bot, or like this Twitter bot. I think it worked on other platforms as well, developed by Microsoft. And the idea was, hey, Tay, now this bot now knows how to speak, but it doesn't know what to talk about. Like, it doesn't have context. And basically, the idea was it got released to Twitter, and the Twitter world was then supposed to feed it with text and like train it by talking to it. And now, if you think about how people have conversations on the internet, maybe especially on Twitter, I think they are even worse. But if you look at people communicate over the internet, and you take that as a baseline, how you want to train someone to have a conversation, maybe in retrospect it's not such a good idea. And looking what happened, it clearly was not a good idea. Within 24 hours, a page got shut down. And the reason was people figured out, hey, I can just say whatever I want to say, and it will pick it up and then learn that behavior. And there are a couple of people clearly abused that and taught Trey to become a racist, anti-feminist. Basically, the worst person that you can be is what this tape was trained to be. Within 24 hours, it got shut down. My favorite is that at some point someone just said, "Hey, you're a stupid machine," and Tay's response is, "Hey, that is correct. And the reason is because I learned from you. And if you tell me dumb stuff, I'll repeat the dumb stuff." And there's now you might say, okay, that is a good example of how we can see that the data that we use to train models has a large impact on how that model behaves. But it's only a Twitter bot. It's not gonna change people's life. It's not gonna impact a lot of people's life. Where I give you the next example, which is the COMPASS system, the correctional offender management profiling for alternative sanctions system, which is still used in the US, which is a system that if you commit a crime in the US, then you are filling out some kind of form. I think it's like 213 questions, some kind of questionnaire that you fill out, and then this data gets fed into this COMPASS system, and then the COMPASS system analyzes it and makes a prediction whether you will be whether you will reoffend or not. So it's basically saying, hey, look, I have this data, and now this person committed a crime, and I make a prediction whether that person will commit a crime again. Like possibly that person has to go to jail, and afterwards I predict this person will commit a crime again or not. And there was a couple of years ago, ProPublica analyzed how this system actually made these decisions and what the outcome of this was. And you can see the result here. And they looked at the skin color, the ethical background of people, and looked at how the system decided whether they would be affected. And there are, if you see on the table, there are basically two ways how you can be wrong, how the system can be wrong. One is you expect the person to reoffend, but the person does not. Or you expect the person to not reoffend, but then the person, when that go, actually does reoffend. And you can see here that the people who were like 23% of the white people were labeled a higher risk, but then didn't reoffend. So it's a false outcome for 23% of the white people, where they were labeled high risk. But the same mistake for African Americans was almost 45%. So there's no difference. Like it's the same questionnaire. The questionnaire doesn't even ask about race. It doesn't ask about skin color. Yet this system has been decided to for 45% of the African Americans to label them a higher risk than they actually were. And on the opposite, labeling someone a low risk and then they do reoffend was 47%, more than 47% for the white people who were under labeled, if you will, and only 28% for African Americans. So there's a clear racial bias in this system, and that system is still being used today. And this system is used to determine bail, and sometimes even to determine like prison sentences. Like the judge looks at this data and then makes a decision. Okay, maybe we want to extend the prison sentence because the assumption is that that person will reoffend. And that is this system has a lot of impact on people's life, and we can clearly see a racial bias. And the reason for that, again, is very likely the data that was used to train this system that then has this very racial bias. There's one more example that I would like to talk about. Autonomous driving vehicles. Not everyone is in agreement when they will take over, but they will probably take over our streets in the next couple of decades, broadly speaking. And how these work is, a lot of them have lots of sensors, but a lot of these sensors are cameras that film the environment around the car. And some systems even only rely on cameras. And what they do is there's some image recognition that basically looks around, and if they see a stop sign, then they identify the stop sign, and the car knows, okay, I have to stop here. Or if there's a red light, I stop, if green light, I can go, and so on, identifying other cars. And also pedestrians, because clearly one of the issues with autonomous driving cars is if a pedestrian is crossing the street, you have to brake. You have to create the least amount of damage that you could do. And now, often this image recognition system, again, is a machine learning model that is trained with data to identify these pedestrians. And there was a study that found out that if you are a dark-skinned pedestrian, you are less likely to be identified by this autonomous driving car as a pedestrian. And therefore, the car is less likely to stop and therefore, or like circumvent or drive around you. And that is, if you think about the amount of cars that we have on the roads nowadays, on a global scale, billions of cars, or a billion cars. If all of these become autonomous driving, and if all of these are suffering from this issue, from this racial bias again, then there will be people will die, and unproportionally dark-skinned people will be affected by this. So this algorithmic bias, this social bias that came in probably again through the data that was used to train this model, because it was probably a lot of data with non-dark-skinned people, lots of white people probably. And this data and that training that was used to then set up this machine learning model will be responsible for this not evenly distributed amount of deaths. And I think that is something where we definitely need to be aware of, that there is a big issue that needs to be fixed before we deploy this on a larger scale. And in summary, I remember this when I was a kid and I wanted something, and all my friends were doing it. And my mother, I asked my mother, hey, can I do it? And she said me, no. And I said, all my friends are doing it. That doesn't matter if your friends are doing it or not. You're not doing it. That is not how machine learning works. Machine learning works exactly in that way. If all my friends are doing it, I'm also doing it. If my friends jump off a bridge, I would also jump. So that is how the machine learning models use that data. And now you look at me and say, Aiko, you've been telling us there's machine learning everywhere, there's AI everywhere, and it fails a lot, and it has horrible implications. The world is on fire. Is there anything we can do about it? And the good thing is, yes, we can. There are, in the machine learning engineering domain, or in the industry, there is a movement nowadays that we want first class, that we want explainability, interpretability as a selection criteria for models. Like if you have a model, you need to understand why it works in a certain way. You need to understand why this input data results in that output data. So basically, we try to address the first issue that I talked about, where it's a black box and we don't know what's going on. We try to figure that out. We try to take explainability into consideration when we choose the model, and make an important point that we need to have this explainability. And I mentioned a lot of the things, a lot of the examples relied on image recognition, which is, I mean, a very powerful use case for particular deep learning nowadays, convolutional neural networks. There's a methodology where you can get more fine detailed information about what is going on in that model. You can see here on the bottom how this image recognition model works, this neural network. Basically, each layer identifies a little bit more information. Like the first layer is just like guess pixels, and the second layer is able to identify edges, and then you get a combination of edges, and then you identify the facial features, and at the end you be able to identify that it is a face or whose face it is. And there's that's just one example. There are other examples that help us remove this black box behavior of machine learning. And in summary, what we would want to do is we want to get away from the standard machine learning model, where we just have data thrown in the model, and then that's how we predict things, and there will be the error. And we want to move into a situation where we have data and we throw it into a model. We look into the model, see how it behaves. We want it to be interpretable. We want to understand it does things that it does, and then add human inspection and retrain it and figure out, okay, look, we missed out this particular set of data. That's why it's making the wrong decisions here. That's why it's making the wrong prediction. Let's train it again with some other data, and basically come to a point where we have human experience as part of the machine learning model training process. And there's another technology which is called LIME that I really like, that helps a lot by doing that. And so LIME stands for Local Interpretable Model Agnostic Explanations. What that means is you can find out, it doesn't matter what type of machine learning model you have, and you can find out for your model and get explanations why it works in a certain way. I'll give you a short example how that works. So what happened here is there's this picture on the left, where there's this picture of a tree frog, and it gets identified as a tree frog with a 0.54 accuracy. And what LIME does is it basically looks at the data and looks at the prediction that gets out of this machine learning model, and then does the same thing, but it removes data points from the input. So as you can see here in the middle, lots of the information is grayed out. So what LIME does is it throws away all of that is grayed out, takes that picture then, and lets the machine learning model predict again, hey, what do you think it is now? And if it is the same prediction, then you know all the data that you had thrown out was irrelevant. If it is a very different prediction, then you know the data you have thrown out was very important to identify it in this case, as a tree frog. And you can see there's and the top one in the middle is, look, you can see that the important is that the eye and the frog mouth gets kept. And even the prediction gets a little bit higher because the bigger part of the image is representing this tree frog now from the perspective of the machine learning model. And if you look in the middle, it looks like the data that is left in the middle is of no indication that it is a tree frog. And then you see on the bottom, there was some things got removed, and still you're identifying it as a tree frog. And if you overlay them and a couple of techniques that you can apply, you can figure out, and that is what you see on the bottom right, you can figure out which part of the input data was relevant for the prediction that it did. And that's why you can get an explanation of why your model worked in a way. And you can do that if you have structured data, if you have tables. You can throw away columns, or you can throw away, there are other things that you can, it's not just picture. It is model agnostic, and it doesn't matter what kind of data you have. You can just throw out some data and then see how it behaves with that data thrown out. Another thing that you can do is have more diverse teams. I mean, it's a common thing in the tech industry that we are not diverse. Other industries are also not diverse. But I'll remind you of the example with the autonomous driving car. I would argue that if there would have been a diverse team, there would have been more people thinking about the diversity of the training data that was used to train the autonomous driving car system to identify pedestrians. And if you have a diverse team, you are way more aware of differences that there are in the real world. And if you are aware of that, you think about it more, and you can add that to the system that you're building. There's another thing that I really like, that is the data ethics canvas, which gets distributed and released by the Open Data Institute. It's basically a guideline of questions. When you're working on a data-centric or a data-intensive project, there are certain questions that it helps you, that you need to ask yourself before starting, that you want to ask yourself to figure out whether you're doing the right thing or not. Just like who this data gets shared with, or what are the limitations of these data sources. And I think that's a very helpful guideline if you're starting this. Sometimes throwing out data is helpful. It doesn't always fix your problems, but if you have a problem where if you try to work on a solution that in no way relies on skin color or on ethical background, why would you then use that data in your data set to train a model? I mean, there's it's easy to put that here on a slide. The truth is that there are often quasi-identifiers where even though you don't have like a name or like something that identifies a person directly. For example, if you would have a data set that does not have my name, but it has my GPS coordinates, and it knows exactly that I always go from this apartment building to that office building, then, I mean, nowadays I don't because I'm working from home. But if you have that information, you could figure out that this data is about me, even though none of the data points actually real is me. So there's quasi identifiers, but there are, in general, if you don't need the data, maybe don't throw it into a system and train the system with it. There's Google Facets, which is a tool that lets you explore your data set. It's relatively easy to use. Just throw in your data set, and then you can play around, and they have really nice visualizations. And within a couple of clicks, you can see if there are some like if you have a data about people, you can easily see, look, only 20% of my data set is actually female. So clearly, I've underrepresented that gender category. Or you can look at age, or you can look at all the other categories, all the other data points that you have, and you can identify whether there are certain categories underrepresented or overrepresented. And that helps a lot to understand the data set that you have. And there's this what if tool, which also works quite well with the previous tool that I mentioned, Google Facets, and it lets you identify how machine learning models work, and gets you a little bit more insights on why decisions were made in the way that they were made by that model. That being said, I hope I could give you some idea of the problems that we are facing nowadays with the especially growing deployment of machine learning models, and that social bias in data, in historical data, social bias in general in data is a big issue, and that machine learning just picks it up and replays that to us. And if we mess up the data, then the model is also messed up. As well as the fact that machine learning models are just way too complex, and that in order to have a correct machine learning model, and that means that we remove these biases, But not only because we don't want to be racist, because it also increases the quality of that model, right? It could be more accurate. So, and in order to do that, we need to achieve a model. We need to have a model that we actually are able to understand and interpret and know why things happen in a way. That being said, thanks very much for your attention. I'm happy for all the questions, if there are any. And if you want to reach
Hello.
Yeah, hi.
Hey, going, great presentation. I was just kind of wondering, like, how worried you are about kind of glitches in these kind of machine learning models being used by, tyrannical or perhaps indifferent to justice governments and kind of organizations. Like, how and kind of what point would you be comfortable with like extended, I guess, machine learning use in society? For example, like like getting fined by like a camera for jaywalking is probably a bit harsh. I don't know. Like it would freak a lot of people out. So I'm just kind of like wondering, like, where do you stand with like the whole, I suppose, like how worried are you about its use, I suppose misuse more, and kind of what other parameters do you think are you would be comfortable with in this area with its like use in society?
That's a great question. I think it depends. I mean, it's so none of like even though I presented a couple of ways how we can get better. Obviously, you wouldn't read perfect. What even is perfect, right? I think the more or less, and that is a very broad statement here. You would want to be better than humans in that situation. And for example, it's really difficult to measure, right? I would argue that you probably want to have some kind of human interaction. Like, I'll give you an example where the the cancer identification. Even though I know that it has outperformed doctors, I would not want to have cancer treatment just because the machine learning model says so. I still want the doctor to look at it again and then see, yeah, maybe there is something. Let's look into that deeper and then identify further and see what's going on. I can imagine that at some point, potentially far in the future, that we reach a point where we have, as a society, the feeling that the machine learning model is safe. And I guess over a couple of decades or maybe hundreds of years, it might come to a point where we come to that. I don't know. I don't know where my threshold is. Clearly, there are a lot of factors. Like I mean, the impact is a factor. There's some kind of risk. If it's high impact, like can it kill people? Obviously, I would be way more cautious than other things that have less impactful. So I think it depends a lot on a case by case basis. For now, I think most of the high impact should definitely have a human intervention. Like I am not convinced that fining people is yet based on jaywalking is on a level where we can confidently say that it's mostly accurate. I do think that a lot of the humans are not perfect either. Like they are like highly imperfect, I would argue, and there are a lot of situations where we can probably now use it to like extend our capabilities. But I think the real power is in fact in what we're looking at decades, or potentially more than decades, to a point where we potentially can reach an amount of accuracy where we can replace humans on it. But I think that is pretty far away. I don't know where my exact threshold is for any particular case.
Well, thanks.
Any more questions? I look at the chat. People remember Tay. I hope people learn from Tay also. I'm also in the Slack channel, so just you can ping me there. or if you want to reach out, I sometimes post Medium things, and I rarely on Twitter, but if I do, so you can follow me there, or can just Google my name. It's actually not common enough. So if you Google Aiko Klosterman, you'll find me. So that's good, I guess. If there are no other questions, thank you very much for your attention. I hope it was interesting, maybe somewhat educational. Thanks a lot.